So hi everyone. So today I will present you results from a paper that was recently accepted for publication in ANA. And in this paper, we have made use of measurements that we have taken by applying X-ray spectral fitting on sources in the 4XMM DR11 catalog in the context of the XMM to Athena project. So, okay. So this is the title of the paper, and these are the name of people that have contributed to this work. So there are 4 topics that we have investigated in this work. The first one is we examined whether the host galaxy properties, and by that I mean the stellar mass and star formation rate of X-ray obscured and unobscured AGN are different. We also examined if the accretion efficiency of the 2 AGN populations differ. We studied the black hole masses of X-ray obscured and obscured AGN, and finally we investigated if there is a correlation between the spectral index, the power law slope of the X-ray spectrum, and the Eddington ratio, which is defined as the ratio of the bolometric AGN bolometric luminosity to the Eddington luminosity, which is the maximum luminosity that an AGN can accrete based on its black hole mass. So I will spend a couple of slides just to show what previous studies have found regarding these 4 topics and what motivated us to revisit them and investigate them again. So as we know, there are different classification schemes that one can apply in order to classify AGN into X-ray obscured and unobscured. One of these classification methods is to use optical spectra to search, for example, for broad lines. And studies that have applied this classification criterion to split AGN into type 1 and type 2 have found that there are no statistically significant differences regarding the star formation rates of the 2 populations, but type 2 AGN tend to live in more massive galaxies compared to type 1 by approximately 0.2, 0.3 dex. And in this plot here, this is taken from a paper we published in 2021, where we used the XMM XXL AGN at redshift lower than 1. And on the left panel, you see the star formation rate distributions, and on the right, the stellar mass distributions. As also mentioned, the similar results were also found in a paper by Zhu et al. In 2018, where they used AGN in the cosmos field. More recently, in a paper that we published with GeorgiosMountrichas earlier this year, and this is also accepted for publication in ANA, we used a different way to classify sources. We used the value of the inclination angle as it is measured through ACD fitting using the SIGAL code. And what we found, in agreement with the previous results that I saw, is that type 2 AGN compared to type 1. But in this case, we also found that the comparison between the star formation rate of the 2 AGN populations, and this difference depends on the X-ray luminosity and the redshift. Finally, another popular way to classify sources is, of course, using X-ray criteria, specifically the hydrogen column density, the NH parameter, to classify sources X-ray obscured and unobscured. And the studies that have followed this classification scheme do not find statistically significant differences regarding the star formation rate and the stellar mass of the 2 AGN populations. And this plots here another paper in 2021 where we used sources in the Buddhist field, and similar results were also found in another paper we published in the same year with Vasilia Masura and Ioannis Georgiadopoulos, and again, we did not find any statistically significant differences. I should note that the NH threshold that was used for this classification is 21.5 in log, but similar results were found when we increased the NH to 22. I should mention, though, that there is this paper by Lanzuis et al. In 2017, where they used data from the cosmos field, so the sources have significantly lower X-ray luminosities, and in which case they found an increase of stellar mass with NH. Now, last year, we published a paper with Ioannis and Ektoras and other authors, and we used AGN in the cosmos field for which we also had information for spectral indices from the legacy catalog, like the H delta and the calcium break parameters, which are proxies of the stellar populations. And we found that an obscured AGN, and in this paper, the difference with the ones that I showed earlier is that we applied a higher NH threshold for the classification. Specifically, we used NH 10 to the 23rd, and we found that obscured AGN tend to live in younger galaxies compared to obscured, using this spectral index that I mentioned earlier. And in agreement with the previous results, we found that obscured AGN tend to live in systems with higher stellar mass compared to unobscured. Perhaps the most important, from a statistical point of view, result of this paper was that obscured AGN also have lower Eddington ratios compared to unobscured. Now, in that paper, we suggested two possible reasons as why there are these discrepant results among the various studies. And we suggest that perhaps one reason is the different NH threshold that is used for the classification. And as you can see in this plot here, on the x-axis is the p-value from Kolmogorov-Smirnov tests, and on the x-axis is the NX cut that has been used for the classification. And for all the difference that we found in all for the various parameters, we see that the p-value increases, so the statistical significance becomes smaller as we lower the NH threshold. Alternatively, we suggested that perhaps the differences among the various studies is because of the different X-ray luminosities that are probed by the various works. And these are two things that we investigated in the paper that I will talk about later. Regarding the other topic that we examined, we all know that there's a strong correlation between the black hole mass and the bulge mass, or the stellar mass, if we talk about high redshifts, where the bulge mass is hard to be determined. And this correlation has been shown by a large number of studies. And also the ratio of these two properties does not evolve with redshift, at least up to redshift of 2. However, what we did in this paper is that we examined these correlations and the relations separately for X-ray obscured and unobscured AGN. And finally, there's this correlation between the spectral index, the gamma parameter, and the Eddington ratio. Even the nature of this correlation, I mean, what is the physical interpretation of this correlation is a controversial issue, but I'm not going to go into the details of that. But many studies that have studied this correlation have not concluded if this correlation exists, or if it exists, if it's robust and universal. So moving now to the actual paper, what we did is we used one of the catalogs that we have compiled in the context of the XMM to Athena project. And specifically, we used one of the catalogs that we have. The catalog that we use has about 200,000 sources with available spectrum in one or more detections in the 4XMMDR11 catalog. And we cross-matched it with a catalog that Hugo talked about in his nice talk earlier this morning, in order to get classifications for our sources. And we ended up with about 75, a bit more than 75,000 AGN. Some of these sources have spectroscopic redshifts, but for the others, we used photometric redshift calculations from Angel's work that he just presented. So we ended up with about 35,000 AGN that either have spectroscopic or photometric redshifts. A bit less than 9,000 of them have spectroscopic redshifts. And by applying X-ray spectral analysis to these sources, and also ACD fitting using the SIGAL code, and using photometry from optical to mid-infrared and to near-infrared and mid-infrared, we ended up with about 2,500 AGN. And then we applied several criteria to make sure that only sources with the most robust X-ray spectral measurements and ACD fitting measurements are included in our analysis. We ended up with about a bit less than 1,500 AGN, about 1,200 lie at redshift lower than 0.5, and a bit more than 200, 212 lie at the redshift from 0.7 to 1.9. So regarding the first two questions, if the host galaxy properties of the obscured and obscure AGN are different and the accretion efficiency of the two AGN populations. These are our results. So in order to classify AGN, prompted by the results of Ioannis' paper that I mentioned earlier, we increased the NH value to the 10 to the 23rd. But the important thing that we also did is that we included in this criterion the uncertainties of the NH measurements. So a source is classified as X-ray obscured if the lower limit of NH is higher than 10 to the 23rd, and as X-ray unobscured when the upper limit of NH is below 10 to the 23rd. And the number of sources we ended up is shown here in the two lenses of these plots. So on the left panel, we see the star formation distributions, and on the right panel, the stellar mass distributions of X-ray obscured AGN shown by the red dashed lines, and of X-ray unobscured AGN shown by the blue shaded histograms. And what we found is that the type 2 AGN tend to have lower star formation rates by approximately 0.25 dex compared to type 1. And the type 2 AGN tend to have higher stellar masses by approximately 0.2 dex compared to an obscured AGN. However, only based on various statistical tests like Kolmogorov-Smirnov tests, Kuiper tests, Mann-Whitney tests, from the p-values that we obtained, only the difference regarding the stellar mass has a statistical significance higher than 2 sigma. And in order to examine the accretion efficiency of the two AGN populations, we used the lambda parameter, the specific black hole accretion rate, which is defined here, which is a parameter that is often used in the literature when Eddington ratios are not available, basically when black hole mass measurements are not available. And so in this case, we see that obscured AGN tend to have lower specific black hole accretion rate values compared to unobscured. This difference is not large, it's 0.1, 0.2 dex, but it has a high statistical significance, as you can see here from the p-value from the various statistical tests. Now, regarding the black hole masses of the two populations, so in order to investigate this, we cross-matched the 1400, about 1400 AGN that we had, and that we used in the previous, the first part of our analysis that I just showed. We cross-matched it with a DR16 QSO catalog of and SEN 2022, and we ended up with 344 sources, and 271 lie at redshift lower than 1.9. We do not use higher redshift because the black hole mass calculations are not as reliable at higher redshifts. And this is the distribution of these 271 sources, the black hole mass distribution, and as a function of redshift for sources with NH values higher than 10 to the 22, shown in red, and lower than 10 to the 22, shown with blue. And this is the black hole mass versus stellar mass plot. And we found, in agreement with previous studies, a strong correlation between the two parameters for the total sample that we had. But we also split it into sources with values, NH values higher than 10 to the 22 and lower than 10 to the 22 in blue and red. And the correlation is strong for both AGN populations. But what one can notice is perhaps that for the same stellar mass, sources with higher NH values tend to have higher black hole masses, at least up to a stellar mass of 12 in log. We also investigate the ratio of these two properties as a function of redshift, and in agreement with most of the previous studies, we found that this ratio is constant up to redshift of 2, with a median value of minus 2.63. And these results here are color-coded based on the NH value of the source in order to see if there is a trend with NH. But this is better illustrated in the right panel, where, as we can see, the ratio for source of the black hole mass of the stellar mass for sources with low NH values, lower than 10 to the 22, is constant, nearly constant, but there is an increase of the ratio with NH for NH values higher than 10 to the 22. Of course, we do not have that many sources with these high NH values, so this is just an indication. But combine this result with the one from the previous slide, these results may suggest that the supermassive black hole growth in the obscured phase is higher than the galaxy growth. And finally, the last question, the last topic that we examined is, as I mentioned in the very beginning, is there is a correlation between the photon index, the gamma parameter, the parallel law slope of the X-ray spectrum, and the Eddington ratio. And here on the y-axis is the gamma, is the parallel slope, and on the x-axis is the Eddington ratio. And for the total population, we find a good correlation between the two parameters. But when we split the sources into sources with low NH, shown in blue, and high NH, shown in red, we see that this correlation is not weak. There is no correlation for sources with low NH values. We also, we checked a couple of things to see if this is a true result. So we excluded sources with a gamma value lower than 1.5 and higher than 2.5, which are unphysical values. And this restriction mainly affects sources with high NH values, and the results remained unaffected. But I should say that when we do this additional restriction, we ended up with only 10 sources with an H value higher than 10 to the 22. So these are the conclusions. So what our analysis showed is that obscured AGN tend to live in more massive systems compared to unobscured, and this difference is statistically significant at a level of higher than 2 sigma. We also found that the star formation rate of obscured AGN is lower by approximately 0.25 dex compared to unobscured sources, but this difference is not statistically significant. And we also found with a high statistical significance that unobscured AGN have a higher specific black hole accretion rates compared to unobscured sources. Regarding the black hole masses, and we found that type 1 AGN tend to have higher black hole mass compared to type, not type 1, type 2, right? I don't remember now. Yeah, type 2. Type 2 AGN have higher black hole mass compared to type 1 for the same stellar mass. The ratio is nearly constant of these two properties. However, our results suggest that the black hole mass over stellar mass ratio increases at higher NH values. And we also, our results show that there is a correlation between the spectral index and the Eddington ratio, but this is only for type 1 AGN with low NH values. That's it. Thank you.
Very much, George. So, any questions we have on the back one?
Yeah, thanks a lot for the talk, Richard Saxton. I didn't quite understand how you're getting the Eddington accretion rate from the to do the correlations and the differences between the two types of AGN. You're not using the bolometric luminosity for that, then?
Oops. You mean here?
Well, everywhere. I mean, so
Okay.
how do you calculate the Eddington ratio?
So yes, I should have mentioned that in the Wu-Sen catalog, from which we got the black hole masses, there are bolometric luminosities. So we use the measurements from this catalog in order to calculate the Eddington ratio. However, I should also say that because in the first part of the analysis, we also use the specific black hole accretion rate, which is a proxy of the Eddington ratio with some caveats, but okay, it's usually used as a proxy of the Eddington ratio. We also repeated this exercise using the lambda parameter, the specific black hole accretion rate. And this gave us the advantage that we had. We also included type 2 sources, since black hole masses are not necessary for lambda. And we also increased the sample that we could use for this exercise. And again, we found a very similar results regarding the gamma and the specific black hole accretion rate, similarly to what we found here.
Okay, thanks.
Okay, so do we have some more questions?
Hi. So I'm not super familiar with AGN, and so with regard to your galaxy properties, I understand star formation rate, mass, luminosity, but I wasn't sure about DN4000, H delta, and lambda Eddington. Are these?
Okay, the ones that I mentioned.
Yeah.
Okay, I briefly mentioned that because. So you mean here in this paper with?
Yeah, on the next plot, this one. Yeah, there was
Okay,
this here I didn't know.
Okay, so basically in this paper with Ioannis and Hectoras, what we as I briefly mentioned, we used sources in the Cosmos field, and we cross-matched them with the legacy catalog that has information regarding the various spectral indices. But the one that we were interested in this paper was the calcium break, and which is a proxy of the age of the stellar population of a galaxy, and the H delta parameter, which basically tells you whether a system has undergone a recent stellar formation burst. So using these two spectral indices, one can discuss about the stellar population of a galaxy, or to compare, as we did here, the stellar populations between different populations. So this result basically comes from comparing these two spectral indices for X-ray obscured and obscured AGN using this and H-cut. And so here, this was just, in this paper, we examined various properties of the two AGN populations. And so this is the calcium break, which is for the age of the stellar population. This is the H delta for the burst, the stellar mass, specific star formation rate, the normalized SFR, which basically the normalized SFR is the ratio of the star formation rate of an AGN, the star formation rate of a non-AGN system with the same stellar mass and redshift as the AGN. And the Eddington ratio, not the Eddington ratio, the specific black hole accretion rate, which is a proxy of the Eddington ratio. And so with the 23rd cut that we applied on NH, these are the p-values that we got from applying Kolmogorov-Smirnov tests. And then when we lower the NH cut to 22 and to 21.5, the p-values increased, which means that the differences that we had detected become less significant in a statistical manner, or even not significant at all. So that was an indication, at least for us, that perhaps the reason why here in these papers that we published earlier, we did not find any differences, because the threshold we had used was 21.5. And as I think I mentioned, when we also increased to 22, again, we did not find any differences regarding star formation and the stellar mass of the two populations. So maybe this is because we should have used a higher NH threshold based on this result here from this more recent paper.
Okay, thank you very much.
Okay, so we don't have some more questions. We have one more quick one.
Hi, George. Matt Page. Just so I understand, when you do your NH cut, the objects that contribute to here are a mix of type 1 and type 2 in the optical?
Yes.
Okay.
There is a mix, yes. Because, the X-ray criteria do not necessarily coincide with the optical criteria.
Okay. All right. Thanks.
Okay, so let's thank George again